So, chapter 11 is two population hypothesis tests. In chapter 10, when we did one population hypothesis test, we had problems where the king and peasant were fighting over a percentage, other problems where it was an average, and other problems where there was standard deviation. So we have percentage, average, and standard deviation problems in chapter 10. In chapter 11, it's the same thing. We just have two populations. So the king and peasant can fight over two percentages or two averages or two standard deviations. When it came to two percentages, there was two different kinds of problems. There was the independent sample version and the dependent sample version. Then last class, we did section 11.3 and 11.2, which was the same thing, but for averages. So there's the king and peasant are fighting over two averages, independent sample version, and then the two population average problems, dependent samples. But those are in different sections. And now what's left is the king and peasant are going to fight over two standard deviations. And that's what section 11.4 is. So it says hypothesis for two population standard deviations. So the king and peasant are fighting over two standard deviations. But unlike the other sections, there isn't an independent sample and a dependent sample version. There's only independent samples. So that's one less thing you have to worry about. Dependent samples only. Okay, there's not going to be an independent sample version. So we're just going to see one version for this kind of problem. All right, so I'm going to go ahead and go through the story, the same kind of story that I always tell you. So here we go. So we got two big bags of numbers. The bag of numbers on the left, we're going to call it population 1 or population 1 data. The big bag of numbers on the right, we're going to call it population 2 or population 2 data. These are two huge sets of numbers, but we don't actually have the numbers in front of us. We wish we had the numbers. So it's like they're imaginary bags of data. We have two huge imaginary bags of data, and sigma 1 is the standard deviation of all the numbers in this bag, and sigma 2 is the standard deviation of all the numbers in this bag, and the king and peasant are going to fight over those numbers. For example, let's say I want to know something about the standard deviation of the ages of all Rio Hondo students and the standard deviation of the ages of all PCC students. So this would be like the standard deviation of the ages of all Rio Hondo students. In order to calculate that and get the answer right, what you have to do is you have to talk to every single Rio Hondo student and ask them for their age. So you need to imagine I did that and all the answers are in this bag. So this is a bag filled with ages. Each number is the age of some Rio Hondo student, and I have the age of all Rio Hondo students, the ages of all Rio Hondo students in this bag. But of course, that's too much work to do to actually talk to 20,000 students and ask them one by one for their ages. So that's why it's an imaginary bag. So we wish we collected that data, and then we could calculate sigma 1, but we don't. So it's an imaginary bag of data that we would have if we talked to every Rio Hondo student and asked them for their age, but we don't. And the same thing with the bag on the right. This would be like the standard deviation of the ages of all PCC students. This bag would contain the ages of all PCC students. That's data we don't collect because there's too much data to collect because we don't talk to, how would I collect the data? I'd have to talk to all PCC students and ask them what their age is. And then this bag would be the ages of all PCC students, all the answers in the bag. But I don't collect all that data, so it's an imaginary bag of data. So again, we have two huge bags of numbers. I wish I had that data. Then we can calculate sigma 1 and sigma 2, which is sigma 1 is the standard deviation of the bag on the left, sigma 2 is the standard deviation of the numbers in the bag on the right. But we don't have the data. So we can't calculate sigma 1 and sigma 2, but the king is going to come along and say, don't worry, I know that sigma 1 is equal to sigma 2. And then remember, we love the king. He's an honest king. We always believe the king. So if he says that sigma 1 equals sigma 2, then we believe him. We're happy. It's like he's saying the standard deviation of the ages of all Rio Hondo students is the same as the standard deviation of the ages of all PCC students. We're like, cool. King said that. We're happy. And everyone is pretty much happy except for the peasant. Peasant comes along and says, guys, he's wrong. King is wrong. Sigma 1 is less than sigma 2. So he's saying the standard deviation of all these numbers is less than the standard deviation of all these numbers. Now, we want to tell the peasant to go away because we believe the king. We love the king. He's an honest king. But the peasant won't go away. He's like, guys, I insist the king is wrong this time. I know he's a nice guy and all that, but he's wrong. Sigma 1 is less than sigma 2. So now we have to decide who to believe. Now, we would know for sure who's right if we could calculate sigma 1 and sigma 2. If we had all this data, we could calculate sigma 1. If we had all this data, we can calculate sigma 2, and then check and see if these are equal. If they're equal, we believe the king. If sigma 1 is less than sigma 2, then we believe the peasant, and the story would be over. But we can't calculate sigma 1 and sigma 2 because we don't have these huge bags of data to calculate it. So what do? We do what you always do in a stats class. You take a sample, but because we have two bags, we're going to take two samples. And we're going to calculate the standard deviation of not the entire bag of numbers, but the numbers in our sample. So we'll take we'll take some numbers out of this bag and we'll calculate the standard deviation of those. For sample standard deviation, we use the letter S instead of sigma. I'm going to call it S1 because it's coming from the bag on the left. Then we're taking another sample from the bag on the right and calculate the standard deviation of those numbers, which is called S2. So like maybe I talk to 50 Rio Hondo students instead of 20,000 of them. I get their ages and calculate the standard deviation. That gives me S1. And then I talk to like 80 PCC students and I get their ages and I calculate the standard deviation of those. That gives me S2. And based on these answers, we're going to decide who to believe. Because S1 and S2 we know because we have the data to calculate it. Okay, so we have two samples, we calculate the standard deviations, and based on those, we decide who to believe. So to settle the dispute, you take two samples, one from each bag, and you calculate S1 and S2. Now, remember that S is your best guess for sigma. What that means is S1 is it might not equal sigma 1, but it's supposed to at least be close to sigma 1 because it's your best guess for sigma 1. And S2 is supposed to be close to sigma 2. So if the king is right when he says they're equal, when he says sigma 1 is equal to sigma 2, then what should happen with these numbers? Well, they might not be equal, but they should at least be close to equal. Okay, like if he thinks both of these sigmas are 10, then this S1 should be close to 10 because sigma 1 is 10. And this S2 should also be close to 10 because S2 is supposed to be close to sigma 2. So these numbers should both be close to 10. That means they should both be close together. So if the king is right, that sigma 1 is equal to sigma 2, then I expect these numbers to at least be close. If they're close, we're going to believe the king. And if they're not close, we're going to believe the peasant. And that's pretty much the end of the story. I'll say a little more. So I lied a little bit, so we'll get to the exact answer there. What if you calculate S1 and S2 and you get that S1 is equal to S2? Are they close together? Definitely, because they're equal. So then you're going to believe the king. Again, all I need is for them to be close together, then I'm going to believe the king. Now, in this situation, if S1 is bigger than S2, this is the situation where even if they're not close together, we're still going to believe the king. Because if you get S1 greater than S2, that's not evidence in favor of the peasant. The peasant is saying less than, and we're getting greater than. So I know they're fighting over different letters, but we only believe the peasant if there's overwhelming evidence in favor of the peasant. But this is not evidence at all in favor of the peasant, so we automatically believe the king, even if they're far apart. But these first two situations are the one you almost never see these two situations in a hypothesis test, because if S1 was equal to S2 or if S1 was bigger than S2, you automatically believe the king, and you wouldn't have to do any rejection region, test statistic. You wouldn't have to calculate all these things to figure out who to believe, because just automatic we're going to believe the king. But the most interesting situation is if S1 is less than S2. If S1 is less than S2, who do you believe? The answer is it depends. You don't say, oh, look, S1 is less than S2 and the king, so we have a less than, S1 is less than S2, the peasant is saying less than, so automatically believe the peasant. You don't do that. Because again, if the king is right, that sigma 1 equals sigma 2, then S1 and S2 should be close, but it could be the case that S1 is less than S2 and they're close. So it depends. Who do you believe? It depends on how close they are. If S1 is less than S2, but they're close together, we're still going to believe the king. So think about it like this. If S1 is less than S2, the fact that we're getting a less than is a little bit of evidence in favor of the peasant, but the fact that they're close together is a little bit of evidence in favor of the king. So we don't have overwhelming evidence in favor of the peasant, therefore we side with the king. The only time we side with the peasant is in this last situation. So if S1 is less than S2 and they're far from each other, then we're going to believe the peasant. And the reason this is true is because, again, if S1 is less than S2, think of it as that's a little bit of evidence in favor of the peasant because he's saying less than. But if the king is correct, then S1 and S2 should be close together. So if they're far apart, that's a little more evidence in favor of the peasant. Now we have overwhelming evidence in favor of the peasant, so we believe the peasant. Okay, so that's the story for what we're going to do today. Does it make sense?
Yes.
Awesome. Okay. A couple more things to tell you, and then we can move on. So remember, the king's claim will always have an equal sign. Okay, so sigma 1 equals sigma 2. The peasant's claim will never have an equal sign. The peasant's claim will either have a less than, or a greater than, or a not equal to. The one it is, it depends on the problem. So you got to read the problem carefully to figure out which one it is for the peasant. I had to pick one for this slide, so I just picked less than. And the other thing to remember is in a chapter 11 problem, there's a lot of writing you got to do in the beginning. One of the things is it's a two population problem. So there's going to be two big groups, usually of people, but not always people, two big groups. Identify those two groups, call one of them population 1, call the other one population 2. Whatever you call population 1, once you've told me what population 1 is, anytime you see a 1 as a subscript, I know it somehow has to do with population 1. And then once you've told me what population 2 is, then anytime I see a 2 as a subscript, like in the sigma 2 or in the S2 or like N2, when we see that, I know that those things come from population 2. And when you write down the hypothesis tests, always make sure you put the 1 on the left and the 2 on the right. So if it's sigma 1 and sigma 2, always put the sigma 1 on the left and the sigma 2 on the right. And the main reason for that is because if you put sigma 2 on the left and sigma 1 on the right, for example, then it might be a left tail test and you might accidentally think it's a right tail test. So just to avoid that little mistake, always put sigma 1, or if it's mu1 or p1 from the other sections, always put that on the left and always put the sigma 2 or the p2 or the mu2 or whatever on the right. Okay, let's keep going here. So again, what are you going to write down when you're doing a problem from this section? First, you're going to identify the populations, you're going to write them down in words. So you write down what population 1 is. So like population 1 might be like all Rio Hondo students, population 2 might be all PCC students. You write that down at the beginning. Then you're going to write down your two population parameters. Today, the population parameters are sigma 1 and sigma 2. You're going to write what those are in words. After you write that stuff down, then you're going to write down your sample information. Remember, we're taking two samples, one from each bag. So we have two samples, sample 1 and sample 2. What information from the samples do we need? We're going to need the sample sizes, okay, which normally we use N, but today it's going to be N1 and N2 because we have two samples. N1 is the size of sample 1, N2 is the size of sample 2. So you'll write down what N1 and N2 are. And then since you have two sets of data, you got to calculate the standard deviation of those two sets of numbers. Sometimes you're going to be given the numbers and you have to calculate the standard deviations. Other times the problem will say, we calculated it for you, here's what it is. But you'll need to know the sample standard deviations. And normally we use the letter S, but because we have two sample standard deviations, it's S1 and S2. So you're going to write all that stuff down at the beginning of the problem. And then after you do that, then you go through your 4 steps in performing a hypothesis test. All right, let's write down some letters. The quantity you're performing a hypothesis for. Okay, tell me, what are the letters that the king and peasant are fighting over in this section? What letters? They're fighting over sigma 1 and sigma 2 today. Okay. Okay, the probability distribution. Okay, so a couple of weird things are going to happen in this section. I mean, it's not that bad, but you might think we would use the chi-square table, because in chapter 9 and in chapter 10, when we dealt with standard deviation problems, we always use the chi-square table. But we're not going to use the chi-square table, so you have to remember this. When it's a two population standard deviation problem, when they're fighting over two standard deviations, we're going to be using a new table called the F table, okay, the F distribution. The table is in my on my website. You know, you click on miscellaneous, and then there's 4 tables. We use the first 3, the Z table, the T table, and the chi-square table, but now we have to use the F table for the stuff we're doing today. F distribution, just so you know, looks like the chi-square distribution. It looks almost the same. So you have to label it. But anyway, you're going to use the F distribution. So again, that's only if it's a 2 population sigma problem, then use the F table. Okay, now, you know how the Z distribution doesn't have degrees of freedom, but the T table and the chi-square table have a degrees of freedom formula? Well, when it comes to the F table, we're going to need 2 degrees of freedom formulas. Well, we have 2 sample sizes, so that's pretty easy. We're just going to subtract 1 from each, and we're going to get 2 degrees of freedom. One of them is called degrees of freedom of the numerator. You don't need to worry about that name that much, but it's df1, which is n1 minus 1. So take your first sample size minus 1. We're going to call that df1. It's also called degrees of freedom of the numerator. Then you're going to subtract 1 from your other sample size, and it's called degrees of freedom of the denominator. df2 equals n2 minus 1. Again, don't worry so much about the name. But you're going to need to know these 2 numbers so you know how to look up things in the F table. You'll see when we do an example in a minute. Okay, test statistic formula. Some of the last couple of test statistic formulas were kind of nasty, but this one in this section is like the easiest one there is. There's the test statistic formula. F equals S1 squared over S2 squared. You just square S1, square S2, and divide, and that's it. No roots, no crazy, nothing, So there's a test format. And again, there's a condition. You don't need to check the condition on any quizzes or exams or anything. But again, I want to tell you a complete story, and it's possible the online homework will mention it. We need essential limit theorem to apply. Remember, essential limit theorem applies to everything we do for the rest of the semester. So as far as standard deviation goes, essential limit theorem basically says we need the bags of numbers to have a normal distribution. Remember on the first slide, I drew 2 bags of numbers. I need those 2 bags of numbers to have a normal distribution. That's what it says here. Population from which samples are drawn, meaning the 2 bags of numbers that we draw the samples from, have a normal distribution. Sometimes in a problem, they'll mention that. And if they mention it, you can just ignore it. They're just mentioning it to let you know, in case you're worried about the condition is true. And in other problems, they don't mention it. And if they don't mention it, we're going to assume it anyway. All right. Okay, we're almost ready to do a problem, but we got a little more weirdness happening. Okay. Well, I told you this before. All samples today will be independent. There's no dependent sample version of the problem. And now here comes the weird stuff. Okay. When you look up something in the F table, okay, I'll show you how to do it in a few minutes, but there's a weird situation here. Let me remind you, in section 10.4, there was one weird situation. It was a one population sigma problem. Let me just write that on the next line. It was one population sigma problem, p-value method, or let me write a two-tail test, and p-value method. This was a weird situation that we saw in section 10.4, and I told you to like put a star next to it or whatever, and just go over it before the exam in case it shows up, which there's a high chance it will show up because a little bit of a weird situation. The reason it's weird is because when you're doing p-value, if it's a two-tail, you got 2 tick marks, and you're supposed to shade the left of the first one and the right of the second one. But there's only one test statistic, so you have to figure out where does it go. Does it go on the left or does it go on the right? And the answer is it depends on if S is less than sigma. If S is less than sigma, you put the test statistic on the left tick mark and you leave the right one blank. If S is greater than sigma, you put on the right tick mark, you leave the left one blank. So that was one weird situation. Make sure you go over that. Now we're going to see 1 or 2 more weird situations. It again has to do with standard deviation problem, but now it's 2 population standard deviation problem. So the other weird situation, there's kind of 2, but we're just going to talk about basically 1 for now. The other weird situation is 2 population sigma problem, rejection region method instead of the p-value method, and two-tail or left tail. This is the other, again, there's a third weird situation that we'll see at the very end today, but it's not that weird, but this one's a little bit weirder. If you're in this situation, then again, it's a little bit weird because here's what happens. When you're looking up numbers in the F table, the number that you look up, they'll only give you the number if it's a right tail test. It's assuming it's a right tail test. So if you're looking up a number in the right tail, then you're good. It's going to be easy. I'll show you how to do it. But if it's a left tail test, if you're looking up a number in the left tail, or if it's a two-tail test, if it's a two-tail test, there's 2 numbers you got to look up. The right one will be easy to look up. The left one will be more difficult. So whenever you're looking up a left tail number in the F distribution, you got to do something weird, okay? So let's read what it says here. When using the rejection region method, the F table will only give you the cutoff number for the right tail. So if it's a right tail test, you can look up the number and you're done. But what if it's a left tail test? So if you're looking up a number in the left tail, what do you do? Okay, it's a little weird. I'm just going to tell you the procedure, and then you just have to memorize it for if it shows up on the exam. Basically, you have to do 3 things to look up the number. First thing you have to do is you have to switch the degrees of freedom. Remember, there's 2 degrees of freedom. Like for example, let's say DF1 is 10 and DF2 is 20. You're going to switch them. You don't have to write it down, but in your mind, you're going to pretend DF1 was 20 and DF2 was 10. So you're going to switch them in your mind. Then you're going to look up the number in the table. Like you're going to pretend it's a right tail test and look up the number in the table. And after you look up the number in the table, that's still not the answer. The next thing you have to do is you have to do You have to take the reciprocal of the answer you got in the table. Basically, you have to do 1 divided by the number in the table. I know it's a little hard to understand without me doing an example, but let me say it all one more time. So when you're looking up a number on the right side of, if it's a right tail test, if you're looking for a right cutoff number, it's easy, just look it up in the table and you're done. But if it's a number on the left tail, you got to do 3 things. You got to switch the degrees of freedom, then you look up the number in the table, then whatever number you get in the table, do 1 divided by the number in the table, and that'll be the left cutoff number. So that's how you look up a left number. And if you're doing a 2-tail test, then you got to do kind of both. You look up the right one, and that's going to be easy. And to look up the left one, you got to go through these 3 steps again. Okay, we will do an example, but any questions so far? Okay, probably need to see an example before things make a little more sense. So here we go. This is the example we're going to do today. Clifford Edelman, a researcher with the Department of Education, followed a cohort of students who graduated from high school in 1992, and he monitored the progress the students made towards completing a bachelor's degree. One aspect of his research was to compare students who first attended a community college to those who immediately attended and remained at a 4-year institution. So before, there's more to this problem, but let me say this much for now. So basically, this guy is looking at 2 groups of students. One group of students went from high school to a community college, then to a 4-year institution, and then got a bachelor's degree. And then the other group of students never went to community college. They went straight from high school to a 4-year and got a bachelor's degree. And he's going to compare those 2 groups. Now, you might think that he wants to compare the average time it takes to graduate. You might think if you go to community college first, the average time it takes you to graduate is a little longer. You might think that was the question, but that's not what he's studying. What we're going to be studying in this problem, they don't show it yet, I'll show you on the next slide, is we're going to study how consistent, I don't care how long it takes, but does this group, like, do the people that go to community college first, maybe they all take, you know, a lot of time to graduate, but do they all take around the same amount of time? Are the numbers all close together? Like this one student took 7 years, this one student took 6 years, this other student took 8 years, but they're all very close. Whereas in the other group, maybe one student took 4 years, one student took 9 years, and they're very spread out. We want to measure how consistent the groups are. Which group is more consistent? Meaning the time it takes them to get a bachelor's degree, are they all close together or are they further apart? Which one is more spread out is what we're going to look for here. Let's go ahead and read the next part. So it says the sample standard deviation time to earn a bachelor's degree of the 268 students who transferred to a 4-year institution after attending community college was 1.162. What this means is he observed 268 people who went from high school to a community college, then a 4-year institution, and got a bachelor's degree. He asked each of these 268 people, how many years did it take you to get your bachelor's degree? So he has 268 numbers, and he calculated the standard deviation of those, and he got 1.162. This number, 1.162, is a measure of how close these 268 numbers are. And again, the smaller this is, the closer these 268 numbers are. Then he looked at another group, the sample standard deviation time to earn a bachelor's degree of the 1,145 students who immediately attended and remained at a 4-year institution was 1.015. So he now looked at a group of 1,145 students. Each one of them went from high school straight to a 4-year institution and then got a bachelor's degree. He asked each one of them, how long did it take you to earn your bachelor's degree? So you got 1,145 numbers. Like, it took me 7 years, it took me 5 years, you know, whatever. And he found the standard deviation of those numbers was 1.015. And this is a measure of how close together these 1,145 numbers are. Okay, assuming the time to earn a bachelor's degree is normally distributed, does the evidence suggest the standard deviation time to earn a bachelor's degree is different between the 2 groups? Use the 0.05 level of significance. This sentence you don't have to worry about. Assuming the time to earn a bachelor's degree is normally distributed. They're just saying that to let you know, hey, the condition, the central limit term condition is satisfied. Once in a while, they'll put that in the problem. And sometimes they won't, and again, we'll assume it even if they don't. So you don't have to worry about that sentence. Okay, and then they say use the p-value method, use the rejection rate method. Okay, what we're going to do is we're going to go through a checklist first. First, I want to know, how can I tell this is a hypothesis test? On the next exam, everything is going to be a hypothesis test. But on the final, you can have some hypothesis tests, some confidence intervals, some probability questions, all sorts of things. So you want to practice recognizing it's a hypothesis test. So first, how can we tell it's a hypothesis test? Then is it a 1 population or 2 population hypothesis test? What are the letters they're fighting over? And then is it independent or dependent samples? So this is kind of like a checklist you should use. You don't have to write any of this down on the quiz or exam or whatever, but you want to go through this in your mind so you can practice recognizing the type of problem it is. First of all, how do we know it's a hypothesis test? Again, sometimes the problem will say perform a hypothesis test, or they'll use the word test, and that's a big giveaway that it's a hypothesis test. They don't say that here, but they do say level of significance. They give you an alpha. They say p-value method. They say rejection region method. And the only time you see those phrases is if it's hypothesis test. So we know it's a hypothesis test. The next question is it a one population problem or a two population problem? Well, this problem, we're studying two different groups. We're comparing two groups. Students that went to community college before they got their bachelor's and students who didn't go to community college. So this is a two population problem. Then what are the letters they're fighting over? When you read the problem, some problems are worded better than others. This one's worded pretty good. They just say standard deviation all over the place. And even if they didn't, there's a question they ask, and you really want to set up your test to answer the question. Here's where the question starts. Does the evidence suggest the standard deviation time to earn a bachelor's degree is different between the two groups? Since they mentioned standard deviation, this is a standard deviation problem. We have two standard deviations because there's two populations. And the last thing is it independent samples or dependent samples? It's independent samples for two reasons. One reason is because the sample sizes are different. When the sample sizes are different, they're always independent samples. And also I mentioned to you in section 11.4, when it's a two population sigma problem, there's no dependent sample version anyway. Okay, so it's going to be independent samples. So now we know what kind of problem we're dealing with. So let's go through the steps. Even though it said do the p-value method, then the rejection region method, I'm choosing to do the rejection region method first this time. On the exam, I'm going to tell you in every problem which method to use. I'll say for this problem, do rejection region method, this problem, do p-value method. So you'll know exactly which method to use. But since we're only doing one problem today, I'm going to do them, using both methods. First thing you got to do is you have to write down what the two populations are. Anytime it's a chapter 11 problem, identify the two populations. Okay, this 268 students are students that went from high school to a community college, then to a four-year, and got a bachelor's degree. That 268 students is a sample. It comes from a bigger group. What group? All students who got a bachelor's degree by going from high school to community college, that kind of thing. I'm going to call that population one. This is going to be all students who got a bachelor's degree. I'm just going to shorten it up by writing down there like the path they took. They went from high school to community college and then to a four-year, and then they got a bachelor's degree. Okay, so all the people that got a bachelor's degree by going along that educational path kind of thing. Okay, and then this 1,145 students, that's a sample as well. That's a sample of students that went straight from high school to a four-year and got a bachelor's. That's a sample, comes from a bigger group. What group? All students who got a bachelor's degree by going that path from high school straight to a four-year. So this population is going to be all students who got a bachelor's degree. By going this route from high school to a four-year. They didn't go to community college. Now, those are the two big groups. Make sure you get the word all in there. You could call this group population one if you want, and this group population two if you want. It doesn't matter. You just got to pick one. And then once you picked it, you stick with it. Since I decided to make population one the students that went to community college, then anytime I use the number one as a subscript, it's going to have to do with students that went to community college. Since I called population two the ones that did not go to community college, anytime you see a two, it's coming from students who did not go to community college. Okay, after you identify the two populations and write them out in words, then you can write down the two population parameters, sigma 1 and sigma 2. Anytime you're writing down what sigma 1 is, or sigma is, the first thing you can write down is the standard deviation. Standard deviation of, and then Remember, standard deviations can only be calculated from a bunch of numbers. In this case, it's if I knew the time each one of them took to get a bachelor's degree, and I found the standard deviation of all those times, that's what sigma 1 is. It's standard deviation of the times these people took to get a bachelor's degree, if I had all that data. So now I'm going to write down those people. The standard deviation of the times all students who, so I'm just copying this down now, who got a bachelor's degree by going along this route from high school to community college to a 4-year to earn a bachelor's degree. Might sound a little bit funny, but it's basically the standard deviation of the times it took these people to earn a bachelor's degree. That's what that says. Okay, so if I had all those times, then the standard deviation of all those times, that's what sigma 1 is. But I don't have those times because, you know, it's how many people have got a bachelor's degree going that route in our existence, you know, might be trillions, you know, quadrillion people, you know. So I don't have those numbers. Now, when I write sigma 2, I'm going to write the same thing, but this part here where I wrote the population, I'm just going to write the other population instead. So this is the standard deviation of the times it took. I'm going to write these people, all students who got a bachelor's degree by going along this educational route, basically from high school straight to a 4-year, to earn a bachelor's degree. Okay. So you write down the two populations in words, you write down two population parameters in words. Then you write down your sample information, sample 1 and sample 2. And as I said, sometimes they're going to give you two big sets of numbers, and sometimes they're going to say, well, we collected the numbers and calculated what you need. Here's what you need. So so what do we need? We need N1 and S1. And for sample 2, we need N2 and S2 in this section. Okay, here's N1. They talked to 268 people who went to community college. They asked each one of them, how long did it take you to get a bachelor's degree? And they found the standard deviation was 1.162. That's what this number is. Okay, so they did the calculation for you in this problem. Then for the other group, 1,145 people they talked to. They asked each one of them, how long did it take you to get a bachelor's degree? And they calculated the standard deviation of all those answers, and that standard deviation was 1.015. All right, so you write all that stuff down at the beginning, and once you've written that down, then you can go through the 4 steps in performing hypothesis tests. Then let's go through the 4 steps. First step, hypothesis tests. So you're gonna write down the king's claim and the peasant's claim. King's claim is going to be sigma 1 equals sigma 2. Make sure you put the sigma 1 on the left side, sigma 2 on the right, and make sure you put an equal sign. Peasant's claim, you're going to still put sigma 1, you're still going to put sigma 2, but you have to decide, do you put a less than, a greater than, or a not equal to in the middle? What do you think?
Not equal to?
Yeah, not equal to is right. Yeah. Because the question is, does the evidence suggest the standard deviation time to earn a bachelor's degree is different between the two groups? It doesn't say that they think one is bigger or smaller. It doesn't say more consistent or varies more or less or whatever. It just says different, so not equal to. Now, normally after you write down H0 and H1, if you use any symbols, I would ask you to write down what they stand for in words. But I had you do that back over here. Here's what sigma 1 and sigma 2 stand for in words. So because of that, we're done with the hypothesis test part. So now we'll go on to the next step. It says rejection region method, so rejection region is second. So for the rejection region, you're going to write down alpha, which is 0.05. And remember, for a test like this, there's going to be 2 degrees of freedom. df1, which is n1 minus 1. n1 on the previous slide, 268. So it's 268 minus 1. is 267. And then df2 is formed as n2 minus 1. N2 on the previous slide, 1145. You subtract 1 from that, you get 1144. So we have 2 degrees of freedom. Then you draw a picture. This is the F distribution that I'm drawing. It looks like chi-squared, so you just draw something that looks like that and label it F distribution. Okay. Now, is this a left tail, right tail, or a two-tail test?
Two-tail.
Yeah, because this is a not equal to. When this is a not equal to, it's a two-tail test. You put a tick mark on the left, go up to the curve, shade to the left. Another tick mark on the right, up to the curve, shade to the right. Now, for rejection region method, what you're going to do now is you're going to label the areas that I'm shading, and then you're going to look up the numbers on the bottom in the table. If it was p-value method, it's the opposite. You would label numbers on the bottom first, and then you would find the areas on the calculator. Okay, so we're going to label the areas first. And the way you do that is alpha is the total area of the rejection region. This is the total of the 2 red areas there. But they have to be equal. So this area here is going to be half of 0.05. You divide it by 2. That's 0.025. Whoa, what did I write there? Yeah, that's 0.025. And this area is also 0.025. So that way the total is 0.05. And now we got to look up the 2 numbers on the bottom in the table, in the F table. Okay, so remember, the one that's easier to look up in the F table is the one on the right. If it's just a right tail, if this wasn't even here, or if it's a 2 table, the one on the right is the easy one to look up. The one on the left is a little weird, but we'll get there. So let's worry about this one here first. Now, when you go and download the F table from my website, there's 4 pages. First thing you have to do is you have to decide which page you have to use. And it all depends on your degrees of freedom. So our DF1 is 267, our DF2 is 1144. Let's go ahead and take a look at the F table. Okay, here's the first page of the F table. Here it says degrees of freedom in the numerator, DF1. Notice the numbers are small, 1 to 8. Degrees of freedom in the denominator, that's DF2, that's on the side. Those numbers are all small again, from 1 to 8. So basically, if both of the degrees of freedom, DF1 and DF2, are small numbers, you're going to use this first page. But ours were both big, so we're not going to use this page. Let's go to the next page. Here's the second page. Now look, DF1 is bigger. It goes all the way up to 1,000. But the DF2 is, again, only from 1 to 8. So you're going to use the second page if DF1 is a big number and DF2 is a small number. But again, that's not the case for us. So let's go to the next page. Here's the third page. And again, if you look at this page, again, the DF1s are all small. The DF2s they go to 1,000. DF2s are big. But again, our DF1 and DF2 are both big. So we don't use this page. So we're going to go to the fourth page. I'm going to remind you, DF1 was 267. DF2, 1144. We're looking for 267 on top. If it's not there, pick the closest one. But don't pick 8. You're using the wrong page if you pick the 8. You want to go to the page where there's big numbers up on top and pick the closest thing to 267. The closest thing is the 120 over here. And then we're looking for 1144 on the side. And again, if it's not there, you pick the closest thing. The closest thing is 1,000. Okay, so now I know that we have to use the fourth page. Okay. Next thing, let's go back. And the area in the tail is 0.025. Okay, so let's remember that, 0.025. Let's go back to the table. So the way I look it up is I start with DF2, the 1,000 that's on the side here. Next to the 1,000, I want you to notice there's a group of 5 numbers. Okay, one of those is the area in the tail that we're looking for. You see the 0.025 right there. So then you're going to go from that 0.025 to the right like this. And then you're going to go down from the 120 until they meet. And it looks like they're meeting at 1.29. That's how you look up the number in the F table, the right tail number. Are you with me on that?
Yes.
Okay. So this number here, 1.29. Okay, we got to look up this number as well. And again, that one's a little bit weird. Let me write down real quick. Even though DF1 was 267, we used 120 for that. That was the closest thing. And we used 1,000 for this one. Use the closest thing on the table. But now, anyway, to look up this number, you need to switch degrees of freedom. Don't switch these though, switch these, okay? You don't have to write this down again, but just, I'll write it down for a second. So we're gonna pretend DF1 was 1144. We're gonna pretend DF2 was 267. So when you're looking up a number in the left tail, you have to switch degrees of freedom first. Then go look up the number in the table. When you switch degrees of freedom, you might use a different page of the table. For us, since both degrees of freedom are big, when you switch them, they're still both big, so we still use the last page. Use the first page if they're both small. Use the last page if they're both big. If if one's big and one's small, use the second page. If the other one's big and the other one's small, then use the third page. So if you're using the second page on one, you might use the third page on the other one, okay? So you might use a different page. But for us, they're both big, so we're gonna go back to the fourth page. Let me go back to the fourth page. And we're pretending that this one is 1144, and we're pretending this one is 267. So we just switched them. All right, so we're gonna look for 1144 on top. It's not there. You pick the closest thing, which is 1,000. On the side, we're looking for 267. It's not there. You pick the closest thing, which is 200. And then once again, you look at the 200, the number on the side here, and next to it, you see there's a group of 5 numbers. Find the area in the tail that you have. The area in our tail was 0.025. And again, you're going to go to the right like this, and you're going to go down like this until these lines meet. It looks like they meet at 1.25. So you switch the degrees of freedom. Then you look up the number in the table. So we got 1.25. That's not the answer still. We only did 2 of the 3 steps. The answer for this number is 1 divided by 1.25. So let me say it again. You switch these degrees of freedom. So you pretend momentarily that these are the degrees of freedom. Then you look up the number in the table. Whatever number you get in the table, you do 1 divided by that number. And that's what the left number is. Okay, so that was a little weird. Are you following me on that? Okay, I'll take that as a yes. Let me know if you have a question. So 1 divided by 1.25, I guess you got to do that on the calculator. When you do it, you're going to get 0.8. Also, one more thing to know. Here, let me write down 1 divided by 1.25. That gave me this 0.8. One other thing to know that's important when we do the p-value in a minute is whenever you have a two-tailed, well, whatever it is, the right tail number is always going to be bigger than 1. The left tail number is always going to be less than 1. The number 1 is always going to be somewhere in the middle, okay, in the unshaded region. The reason I know that is because the test statistic formula was S1 squared over S2 squared. So remember the first slide today? It was like how you can decide who to believe. You take 2 samples, you calculate S1 and S2. If S1 is equal to S2, who do you believe? If S1 is equal to S2, you believe the king. But if S1 is equal to S2, then S1 squared is equal to S2 squared. So the top and bottom numbers are equal. So when you divide them, you get 1. So if you get a test statistic of 1, you believe the king. Because if you get a test statistic of 1, S1 is equal to S2. You believe the king in the unshaded region. So that tells me that the number 1 is always in the unshaded region. Okay, so that's something to know. Number 1 is always in the middle. So if it's a right tail test only, that number is always going to be bigger than 1. If it's a left tail test only, that number is always going to be less than 1. If it's two-tailed, the left one's less than 1, the right one's bigger than 1. The number 1 will be in the middle in the unshaded region somewhere. Okay, just something to know. All right, I'm done with the rejection region part of this problem. Any questions? All right, so then we'll go on to the third part, which is the test statistic part. Normally in the test statistic part, I have you write all your sample information, but we wrote that back here. Okay, all the sample information is here, so you don't have to rewrite it. It's already there. So you can just plug into the test statistic formula. Test statistic formula is S1 squared over S2 squared. Go back. So here, S1 is 1.162, S2 is 1.015. 1.162 squared, 1.015 squared. And you calculate that number. Let me do that real quick. And I'm getting 1.3106, 30202. Okay, so that's how you do the test statistic. Then you go and check to see where does your test statistic land in your rejection region picture. So I'm going to go back to the previous picture. Remember the number was 1.13, no, the number was 1.3106, 30202. It's bigger than 1.29. It's 1.3 something. So we land in the rejection region. Since we land in the rejection region, that means the conclusion is that we reject H0. Okay, then we have to write the answer in words. So what does reject H0 mean? Reject H0 means we're not believing H0 anymore, we're believing H1. You want to say evidence suggests whatever H1 is saying. But the king is saying that the standard deviations are equal, and the peasant's saying they're not, they're different. So evidence suggests these standard deviations are different. But I'm going to just answer the question. The question says, does the evidence suggest the standard deviation time to earn a bachelor's degree is different? Which is what the king is saying, that they're, that's what the peasant is saying, they're different. Does the evidence suggest that? Yes. Evidence suggests that they are different. Okay, so that's what we're going to write here. Evidence suggests now I'm just going to copy what it says right here, that the standard deviation time to earn a bachelor's degree is different between the two groups. Different between the two groups. And that's how you do this problem using the rejection region method. Any questions? All right. So then last thing to do is, how do you do this problem if I ask you to do it using the p-value method? That's what it says here, p-value method. So again, you're going to have to go through 5 steps, right? You write down the stuff at the beginning, and then you go through your 4 steps. Because we did most of it already, I won't do it over, but I'll just outline what you would do. So I'll call this step 0. That's where you write down the populations, and you write down what sigma 1 and sigma 2 are, and all that stuff. So you do that first. We already did that, so I'm not going to do it again. Then you write down the hypothesis tests, which we already did, so I'm not going to do that again. If it's p-value method, the next step would be the test statistic part, which again we already did, so I'm not going to do it again, but I will remind you what the answer was. The answer was 1.310630202. And then the next step would be the p-value part. We did not do that part yet, so we'll do that part now. For the p-value part, you write down alpha, which is 0.05. And the 2 degrees of freedom, df1 was 267, df2 was 1144. Then you draw a picture. Again, this is the F distribution. Make sure you label it. And this was a two-tail test. So you put a tick mark on the left, you go up to the curve and shade to the left, put a tick mark on the right, up to the curve, shade to the right. All right, now, again, the reason the p-value differs from the rejection region is these areas are not the same areas, and the numbers on the bottom are not the same numbers, but otherwise it looks like a two-tail picture. So the picture looks kind of the same. What you do is you have to put the test statistic in the picture. But so this is another slightly weird situation. It's not that hard though, but we only have 1 test statistic, but we have 2 numbers to label. So do we put this number on the left or do we put it on the right? So I want you to remember, just like the chi-square table, the F distribution doesn't have any negative numbers. So it's not like this number here is 1.31 and this number here is negative 1.31. It doesn't work that way. Just like the chi-square table, the number is 0 right here at the beginning. So there's only positive numbers there. So we have to decide, do we put the test statistic on the left or the test statistic on the right? And the way you're going to remember it is, remember the number 1 is always in the middle, in the unshaded region. So if you get a number bigger than 1, you put it on the right. If this test statistic is less than 1, you put it on the left. So the number here is 1.3106300202 because it's bigger than 1. Okay. What do you put on the left? You can just leave it blank. Okay, you with me on that much?
Yes.
All right. Then we're going to write down the notation for the p-value. Normally for the p-value notation, you would write the notation for this area and then the notation for this area and then add them. But I can't write the notation for this first area here because I don't know the number down there. So what we'll do instead is we'll just write down the notation for this area here on the right and then multiply it by 2 because the two areas are the same. The notation for this area is going to be probability. You're going to put an F because it's F distribution. Greater than, because we're shading to the right, 1.3106300202. And then you multiply by 2. So 2 times that. Okay, there's a notation. Now let me get the calculator out so we can calculate it. Whenever you calculate p-values, you do it on the calculator. And the way that you do it is you would go second distribution. So it's like over here. So you go second and distribution. Distribution is right above this. It's this vars button, but right above it in blue, it says distribution. So you go second distribution. And because it's F distribution, you're going to go down to the one that says FCDF. Okay, don't ever use the PDF one. Use the FCDF, and it's the one that says F because it's F distribution. So you go there. Let me clear all that out, even though that's the right answer there. All right. Now, again, the way we're going to type this in is we're going to ignore the left area. We're going to type in the right area, get the answer, and then multiply it by 2. So let me cover up the left one. You got to tell the calculator the lower and the upper. The lower is the left edge of the area, which is this 1.31 number, 1.3106300202. Then the upper is the right edge, but this right edge goes on forever to infinity. So the way you type infinity is you type a really big positive number. And then you put the 2 degrees of freedom in, and you got to put them in the right order. DF1 first, oops, well, we could leave that. That's okay. 267 and then 1144. I know this is just 99999, but adding the 26 just makes it a bigger number. That's okay. So you have to put them in the right order. I know at some point we switched them. Don't switch them. Okay, it's the original degrees of freedom order. And then enter, get the answer. That is not the p-value. That right there is the area for just the right tail. But the left tail area is the same as that. So if we had the left tail and the right tail, it's like multiplying this answer by 2. And that's the p-value, 0.0036. Okay, so the answer is 0.0036. And then after you have the p-value, always ask yourself, is the p-value less than alpha? 0.0036 less than 0.05. And the answer is yes, it's definitely less than. It's 0.00 something, less than 0.05 something. So then you would go to the conclusion. The answer is yes, the p-value is less than alpha. The conclusion is rejected 0. Just like it was doing it the other way. And then you would write it in words, which I already did, so I'm not going to do it again. And that's how you do the problem using the p-value method. All right, well, that's the end of the story for today then.